Okay, section 4-5, we are talking about derivatives and how they create shapes and shapes of graphs. So there's a couple of things that basically we're graphing stuff in this section, and derivatives, there are some things that you can do to help you sketch the graph. We did a preliminary set of sketches of graphs in pre-calculus where we calculated the y-intercept and x-intercepts, and what we're going to do now is we're going to add to those sketches by calculating mins and maxes and points of inflection. So the first thing that we do is we can find intervals of increasing and decreasing. Okay, and this is called the first derivative test. So here's kind of your steps. The first thing that you're going to do is you're going to find the derivative of your function. Second thing is you're going to set it equal to 0 to find your critical points. Third thing is you are going to create a number line with the critical points. And the fourth thing is we're going to test the intervals on the line to find slope, direction, slope and direction. Okay, so let's walk through an example. Directions will say just find it. Sometimes they say use the first derivative test, and other times they just say find the intervals where the function is increasing or decreasing. Increasing and decreasing, and in addition it can ask you to find all extrema. So all the mins and maxes, basically. Alright, so let's go through our steps. First thing that we're going to do is find the derivative. So f prime of x equals negative 3x squared plus 3x plus 18. Okay. Then we're going to set the derivative equal to 0. And what we're doing again is we're finding the places where the slope of the tangent line is 0, and those are the mins and maxes, potentially. Alright? Negative 3x squared plus 3x plus 18. And we can go ahead and factor that. If it doesn't factor, you'll need to run it through the quadratic formula. And always the quadratic formula always works if you prefer that. So this is going to be a negative 2 and a 3. So these are your critical points. Okay, that's step 2. Then our third step, I'm just labeling these for reference for you. I don't need to see all that in your work. I mean, you can just do it all together. That's fine. Next, we're going to create a number line. Okay. And our critical points are our markers on the number line, and what they do is they're dividing this number line into sections. So it creates 3 sections. And by the way, anytime that we're drawing a number line, we're actually it's an XY coordinate system. We're just drawing the x-axis. So there is a y-axis going here, and you could graph this on your graphing calculator. And that's a great way to do it if you want to look at the signs there. So I'm gonna do it by plugging in points, but you can use your calculator if you choose. So you're gonna pick a point, a test point in each of these regions. Okay. So like for example, I'm gonna pick negative 3, and again, what I want to know is what is the slope of the tangent line. So I'm not plugging it into the original equation f. I'm plugging it into the derivative. I find it easiest to plug it into this factored form, but you can also come up here and plug it into the original if you want. It doesn't matter, they're all equivalent. And again, all we want to know is what's the sign. So I plug the -3 in, and I say, okay, that first quantity is going to be positive when I plug in a -3, and then the second quantity is going to be negative. And so that gives me a negative product. Okay, then I'm taking 0, I'm going to plug it in here, and I get a -6, so that's a negative times a -3, and that gives me a positive product. And then I'm going to choose like a 4, and that's going to give me a negative value in the first factor, a positive in the second, and so that's going to give me a negative all over. Alright, so here's what's happening. If the slope of the tangent line, which is what we're finding, is negative, okay, slopes of tangent lines that are negative go down from left to right. And so that is a decreasing function. If the slope of the tangent line is positive, those lines go up from left to right, and that is an increasing function. So what this sign chart is telling us is the intervals of increasing and decreasing. Okay, so I can answer part of the question now. This graph is going to be increasing from -2 to 3, okay, and it's going to be decreasing on the outside section, so -infinity to -2 and 3 to infinity, this section and this section. Okay, now let me draw a little sketch. I'm just going to draw, it's not an accurate sketch or anything, it's just going to be showing you what's happening. If I am increasing, let's just extend this number line down here a little bit. If I'm increasing on this whole interval, okay, and then I'm decreasing on, please hold. I'm decreasing on this left interval. So that means I'm coming down. I might, it's not necessarily a straight line, but I'm coming down somehow. And then I'm increasing in this middle section, and then I'm decreasing in this right-hand section. Look at what happens. In order to decrease and then increase, what you're doing is you're creating a minimum, because it goes down and then up. That creates a minimum. If you're increasing and then decreasing, you are creating a maximum. So the way that you find those extrema they are the critical points. They're the turning points from increasing to decreasing. Okay, and if you're going down up, you're making a min. If you're going up down, you're creating max. Okay, so your minimum is going to be at -2. Okay, and you're going to get a maximum at 3. And the question is, what is the minimum and the maximum? And that means a y value when I'm asking what is it. When I ask where is it, it's an x value. When I ask what is it, it's a y value. And so the way that you find the y value is you have to plug this x value into the original function. Now this gets confusing for people because they want to plug it back in the derivative, but you have to remember what you're trying to find. You're not trying to find a slope now, you're actually trying to find a value on the function. So if I want a value, I have to go up to this original here. So in order to find my minimum, I'm going to plug in f of -2 into my original equation. Hold on. So it's -2 cubed plus 3/2 times a -2 squared plus 18 times a -2, and that ends up giving you, I think it's -22 if I did my math right. Okay, and then when I plug in 3, I get 3 cubed plus 3/2, 3 squared, 18 times 3, and I got 81/2 out of this guy. Okay, so to answer the question, here's the first part. I'm increasing on and decreasing on those intervals, and then I've got a minimum at -2 of -22, and I've got a maximum at 3 of 81/2. And the minimum should be lower than the maximum. Just check that, make sure you're doing that right. Okay, so what this does is it gives us more information about the graphs. In pre-calc, we talked about how to take this and find the x-intercepts. You do synthetic division, you factor it, you find those x-intercepts, and then what the calculus is doing is it's telling us where are the mins and maxes, and when are we going up and when are we going down. Okay, so you can check your work by graphing on a graphing calculator. That's just fine with me. I do want to see the algebra behind the work. Okay, so if you want to pause this video and try one, example 4.17 in your book is a great one that's kind of similar to this to try. Pause the video and go do that. All right. I'm going to do one more of these before we go to the second derivative test. So find all local extrema for f of x equals the cube root of x minus 1. All right. So just wanted to do something that doesn't look entirely like a polynomial. So here's your directions. I could say do the first derivative test. I could say I want intervals of increasing or decreasing, or I could say find local extrema. These all walk you down the same path of this list that I gave you right here. Okay, so what I recommend is throw those directions on a note card, put the list on the back, and memorize them. Because half the problem is figuring out what do I do on a problem. Okay, and so memorizing the directions is actually a pretty valuable study tool. All right, so here we go. And if you don't have a list in your head of what you're going to do, then you haven't memorized enough. Okay, you have to memorize that list so that you have a game plan in your mind. So the first thing that I want to do is I want to find f prime of x. All right, so I'm going to take the derivative. This is a chain rule. So maybe we want to rewrite it before we do the derivative. Maybe we want to rewrite it with a fraction exponent so we can see that a little bit better. And now we're going to take the derivative, chain rule. Derivative of the outside function evaluated at the inside function times the derivative of the inside function. Okay, and if we want to write that back in root form, this guy's going to go downstairs, and it's going to be 1/3, and it is the cube root of x minus 1 squared. Okay, whichever format you like is fine. Okay, now, critical points. Critical points are points where f prime of x equals 0, or where f prime of x is undefined. All right, so in this situation, f prime of x does not equal 0 because the numerator is 1, and so the top is never going to be 0. Remember, a function is 0 where the numerator is 0, and it's undefined where the denominator equals 0. So I look at anytime you have a rational any kind of fraction function, you look at the top to get your 0 points and your bottom to get your undefined points, and you can pull those out independently. So what I'm thinking in my head is, well, 1 doesn't equal 0. Okay, so there's no critical points off of that piece. So let's take the bottom and figure out where is this equal 0 to figure out if I have any other critical points. So I'm going to divide through by 3 first. 0 divided by 3 is 0. I'm going to cube both sides to get rid of the cube root. 0 cubed is 0. I'm going to square root both sides. 0 rooted is 0, and I'm going to add 1. Now you probably could have, maybe you see that right away. If you do, you don't have to walk through all the steps. I just want you to see how I'm undoing it a little bit at a time. So this is my only critical point. It's an undefined value for the function. Okay, so I'm going to put my 1 here. Okay, and I'm going to test values now. I'm going to take value to the left of 1, let's say 0, that's a nice one to do, and I'm plugging it into my derivative because I want to know what's the slope. So that's going to be 1 over this thing right here gets squared, so that's always positive. And the 3 is always positive, and the 1's always positive. So no matter what it looks like, no matter what I plug in here, I'm going to get positive values. There's no way a negative's coming out of that thing. Okay, so what this means is this function is actually entirely increasing. Okay, so it's increasing on negative infinity to infinity. So where are the extrema? There aren't any. Because in order to have an extrema, you have to go up and then you have to go down again. And we're not. We're continually on the incline. So this has no extrema, no local extrema, let's say. Okay? So don't get weirded out if there's no answer. That happens. Okay, now, what does this function look like? If you remember from pre-calculus, the cube roots are the inverse functions of the cubes. So what they are is it's a cube, it's a sideways cube root, and it's laying down on its side, something like this. And I think it shifted. It looks like it shifted right 1 because that 1's in there with the x. Cube roots are the cubics, so let's just call this 1. It shifted right 1. You don't have to draw the picture, but I think the picture has some value as you're going along. It's worth graphing things and just taking a look, just to confirm what you see. Yes, this function is, as I go from left to right, this function is always increasing. I'm on the roller coaster on the left, and I am continually going up. I mean, maybe shallowly going up, but it is a continual up. So there's no min-max there in that scenario. Okay. Next problem. If you want to do another example of this, if you want to pause and do an example, you can do example 4.18. Okay, in the book, you can pause this right now and try that. If you feel like you've got the first derivative test, then let's move on. The next thing we're going to do is find intervals of concavity. And this is the second derivative test. So once again, let's make a little list of directions first of all. If I say do the second derivative test, if I say find the intervals of concavity, or if I say find my points of inflection, we'll talk about those in a second. These are all the same kinds of directions that lead you down this list. Now, the interesting thing, and why this is a really fascinating section, but why it can get confusing is the list for the second derivative is exactly the same as the first derivative test. It's just with the second derivative. Okay, so it's going to be find f double prime of x, second derivative, set f double prime of x equal to 0 to find the critical points. Okay, make a number line with the critical points, and test the intervals to find concavity. And let me compare with my previous list. Yeah, there you go. It's the same. I use a little different language, but it's the same. Okay. So let's do an example of this. The first example that we did, we'll do that again. We'll just take it a little further. Because some of the homework problems and test problems could just give you one function and tell you, I want all the stuff. I want increasing, decreasing, extrema. I want concavity up and down and points of inflection, which just means you run the test twice. So let's do the first step. F prime of x is negative 3x squared plus 3x plus 18. And then my second derivative is going to be negative 6x plus 3. Okay, I'm going to set that equal to 0 to figure out my critical points. So I get x equals 1/2. Oh, I said 1/2. Hand wrote 1/3. Okay, now, just like up in the first derivative test, these critical points are your min-maxes. This is where we get our points of inflection, but these are possible points of inflection. I write POI for points of inflection, okay? Points of inflection. Just like, okay, let's look at the previous problem. Look, this was a critical point, right? But it turned out that it wasn't a min or a max because this whole thing was increasing. So these are possible min or max, but don't have to be. And the same is true for the critical points on the second derivative test. They're possible points of inflection. So here's our number line. 1/2. I'm picking values on either side. And again, I'm plugging into my second derivative. Okay, and I plug in 0, I get positive numbers. I plug in 1, and I get negative numbers. Now, this is what it means. A positive value on an interval means that the graph is concave up. Makes sense. Positive is up. So this graph is going to be concave up on negative infinity to 1/2, and it's going to be concave down anywhere the interval is negative. So from 1/2 to infinity. Now what does this mean? Concave up is just a bowl up. Concave down, bowl down. Okay, so it's concave up means it's caving up. Concave down means it's caving down. And a point of inflection is a place where the graph changes from concave up to concave down, or vice versa. So it's not, the order doesn't matter. It's just a place where, it's going to go from this to this. It's that point right there. And generally, there are some weird graphs out there, but generally if it's kind of a well-behaved graph, that point of inflection is halfway between the max and the min. If it's not skewed and stuff, but if you're looking at kind of a smooth polynomial curve, that point of inflection is in the middle there. Okay, so graphically, if you look at this guy, this point on our previous problem, this is actually a point of inflection. If you ran the second derivative test on it, you'd find that that is true. Look at the graph. To the left of this point of inflection, it's like this. That's a bowl up. Okay. To the right of the point of inflection, it's like this. That's a bowl down. It doesn't have to be a whole bowl. It can even be a half. It's just that it's a curve up or curve down. So if you run the second derivative test on this previous problem, you will actually find your number line will have 1 as its critical point, and to the left of 1 you'll get positive values, to the right of 1 you'll get negative values. That might be worth pausing and doing if you want to try that and verify that that's what you get. Okay, so for the problem that we are doing, we found that it's concave up to the left of 1/2, concave down to the right of 1/2, and because these signs change, that means that 1/2 is a point of inflection. Okay, so I would say that I have a point of inflection at 1/2. And if I want to figure out what the coordinate is, I am going to have to plug that all the way up into my original function. Remember, keep your head on screwed on straight. If you want to, the second derivative finds concavity, the first derivative finds increasing, decreasing, and the first function finds the actual point. That might be worth writing. So this is where I find points, if I want a y coordinate. This is where I find increasing, decreasing, min-max. And this is where I find concave up and down and points of inflection. So make sure you're plugging it into the right function for what you're trying to find. So I plug in 1/2. It's a big mess. I think I calculated it and wrote it down here somewhere. It ends up being 37/4. So f of 1/2 equals 37/4, assuming I cranked that out right, but you can verify that. So I've got a point of inflection at 1/2, 37/4, right there. Okay, so that would be the answer to the question, would be this part, my intervals and concavity, and where my point of inflection is. Okay, now I'm not going to do another example of this one, but let's just say, for example, that you were doing, you are finding intervals of concavity, and you did all your work. Okay, you found your second derivative, and you found your critical point, and you tested, and you got like plus plus, or let's say you had 2 critical points. Okay, you got plus plus minus or something like that. What this means is I'm concave up on this interval and I'm concave down on this interval. This is not a point of inflection because the graph did not change on either side of it, but this one is a point of inflection because it did change from positive to negative on either side of it. Okay, same's true with the max-min. All right, try these. I think they're kind of fun. The derivatives are significantly less horrific than they were in the beginning of chapter 3. So the calculus part of it is pretty easy. And make sure you get out your graphing calculator, take a look at things, orient yourself so you know what's going on. All right, I'll see you next time.